So, can you hear me again? Good. Okay, thank you. That was a strange thing. Okay, but we are almost through with it. So the characteristics, they must not adversely affect the clinical condition and safety of the patients in a way, let's say, that is stronger than if he would do nothing. But under any circumstances, not of other persons. And important is over the lifetime of the device anticipated by the manufacturer, where the device is subjected to stresses which may occur during normal conditions of use. That is always important because in the specification you have to describe what are the use conditions. And for instance, you know, in a body of humans you have a certain temperature of, let's say, 36 to 40 degrees centigrade. That is normal. You have a humidity of 100%. You have electrolytes. You have ions and so on. And these are the surrounding conditions. Also, a patient, for instance, he may jump or do sports, so you have a certain G level, accelerations, and so on and so on. Sometimes you also can find some plate on a laboratory room where you see the sign heart pacemakers not allowed here. So people with pacemakers cannot enter or may not enter because the strong electromagnetic field might compromise the function of that pacemaker. But these are things which are laid down. And another thing is the device must be designed, manufactured, and packed in a way that their characteristic and performances are not adversely affected in the storage and transport conditions and even in the implantation conditions in the operation room. That means you cannot say just, I specified it, but what happens on the way from the storage in the manufacturer's company to the storage in the hospital, that doesn't apply to us, yes? But we have a certain life cycle for the product, and normally safety must be treated from the very beginning to the very end, or you could also say from the cradle to the tomb of that device. And now requirements regarding design and construction. Devices must be designed and manufactured in such a way as to remove or minimize as far as possible risks connected with the use of energy sources, especially electricity, insulation, leakage currents, and overheating. So imagine we have a pacemaker. It has a battery for, let's say several thousand milliamp hours or even amp hours, yes. And if you have 1 amp hour of energy in it, that's a lot. And if you would release that in a minute, the temperature would increase significantly. So especially energy sources are something which is very risky. risks connected with reasonably foreseeable environmental conditions, such as magnetic fields, as I mentioned, external electrical influences, electrostatic discharge. Normally it's not so important as long as you do not have any wiring going outside of the body. Pressure or variations in pressure and acceleration. So that means if the person is doing bungee jumping and deep sea diving, then possibly not all of these actions have to be covered by the specification of the device. But what is reasonably foreseeable, or sometimes it must be excluded, like do not go into rooms where we have strong electromagnetic fields. Risks which may arise where maintenance and calibration are impossible, including excessive increase of leakage currents, aging of materials, and so on. That means normally a device that is implanted cannot be recalibrated. So if the device in some way uses the temperature in the body, or it uses the pressure in the body, for instance, you measure blood pressures or something like that, you cannot calibrate it in an absolute way. Yeah, maybe you can get some guess, or for instance, a modern analog digital converter has at least an electrical reference voltage on board, so at least it can be calibrated electrically, but not with respect to the physical property. And that must be taken into account, and that means it must be absolutely clear that the characteristic curve of a sensor, for instance, must not change over time. Sometimes not only inputs are calibrated, but also outputs can be calibrated. That means it is not possible, so the devices must be stable over time, and their input and output must not change, for instance, just according to aging or such a thing. Also, you cannot repair an implanted device. The devices must be designed and manufactured in a way as to guarantee the characteristics and performance. And here several aspects have to be treated. One is the materials used, particularly as regards toxicity aspects. That's the reason why especially two groups of materials are used very frequently inside bodies, or let's say three groups. From the metals, it is titanium for the shell of an implanted device, for instance, gold, often for electrical conditions, but also sometimes for structural parts, for instance, gold teeth you have. These are not toxic. And another group of materials is silicones. Silicones are often used for, let's say, cosmetic purposes. So the cosmetic industry implants lots of silicones, but on the other hand also implantable electric devices often contain silicones because silicone is compatible with the body. And that's important, mutual compatibility between the materials and the biological tissue. That means two things. One is the material must not be toxic or in other way have a disadvantage for the bodies. That also can be if the material is too hard and has too sharp edges, that could lead to some reaction of the body. On the other hand, the substance that is implanted must not be harmed by reactions of the body. Yes. So if the human body forms some antibodies, and then some attack cells start feeding on the housing of the device, because for instance it's a polymer device, then of course that would also be not good. So it's a mutual compatibility. And the third is when there are substances inside the housing of the implant, also the substances inside must not harm the device. The quality of connections, so that's my job. Assembly and packaging and interconnection must be made in a way they are safe. The reliability of the source of energy we have seen, and if it is a hollow shell and has something inside or is hollow inside, it must be leak proof. So nothing must leak in and nothing must leak out. And now there is something which is important. There are more aspects. So now imagine you have a company making heart pacemakers, and these pacemakers have been developed. And now you want to produce these pacemakers in your factory. But the question is, how can you get into the market with that product? And first of all, you cannot have any company producing that. You cannot just say, okay, my doctoral thesis was so good, I now open a company, I have lots of know-how for my PhD, I open the company and I make a certain brain pacemaker, for instance. So then you can found a company, but that company must have a complete quality assurance system. As I mentioned, ISO 9000, but derivative that is so the ISO 9000 is the basic quality management system, and you must prove you have implemented such a system in your company. If you do medical devices, you have a certain quality management for medical industry. You have other quality management system for aircraft industry, for instance, and so on. The manufacturer shall apply the quality system approved for the design, manufacture, and final inspection of the products concerned as specified in sections 3 and 4, and shall be subject to EC surveillance as specified. So in somehow the European Commission must have surveillance over this, but typically not directly, but via subsidiary organizations. So that is the company. The second is, yes, there is some kind of, let's say, quality philosophy. You could say, for instance, if you have a very good company, you can just rely on that company. That means you are sure that company, all they will do will be good and safe, and in that way you do not have to give instructions, or you do not give legislation or directives for the product. You just give a directive. The company must be good in a way. It has an excellent quality management system, and then you rely. You will rely on the product, on the pacemaker, for instance. So, would you rely on it? I don't know. Maybe you could, but it's better to have more legs to stand on, or better to have redundancy. And that means you have a type examination for the device. It is a procedure where a notified body observes and certifies that a representative sample of the production envisaged satisfies the relevant provisions of the directive. A notified body, that is something like TÜV, Technical Überwachungsverein, or some other organization that has been accredited. So they are allowed to check, yes? In this law here, it is called a notified body. In German, it is eine sogenannte benannte Stelle, but just keep in mind, it is TÜV or something like that. Or in America, Underwriters Lab, or some organization working for the FDA in America, and so on. Okay, and here, that means that's a procedure under which this notified body observes and certifies it. Another thing is the verification. That is the act by which a notified body verifies and certifies that products conform to the type described in the EC type examination certificate. So there is a type examination. You could say you have a specification, and then it is verified that the product is in accordance with that. And that means we check whether it is saved, and for that verification we have several steps, and one of the most important steps is that the risk assessment and management. Again, the risk assessment is not done here, but the risk assessment has to be done in the development phase. Here in the verification, it is just verified what the outcome of such risk assessment and risk management is. And in that way, after we have that, the device is in some way cleared. That verification is done both on paper and on real devices. For the hardware, it is important that the hardware is not just prototypes, but hardwares have already to be produced on series machinery, on a factory which is capable doing series production. So you cannot just build some prototypes in lab and give them to the verification. It must be prototypes according to your normal, regular series production. At least for the series production, which has to be built up for that equipment. So you could say you either produce it on series production, where you, for instance, produce many types of pacemakers, or you build up a new factory. On the other hand, for that new factory, you again need the declaration of conformity that your factory is according to the ISO quality management standard. Okay, and that is that means check the design and the implementation of the design. After that, you could say, okay, that has been verified, that the type investigated is conform with European directive. And then you go into series production. Something is important. Here you have to declare conformity of type. You had the type examination, and when you produce, you must make sure that nothing is changed in that process. That means you must not make any improvement and just you think you improved it, but you at least have to check and also you have to go back to the notified body in order to get clearance for that. So they want to see, I improved it here, did I make it worse in another place? So when you hack around with software, you can easily improve software in some performance parameter, but you can easily introduce other errors here. And in that way, you must check whether that be. And that means you cannot just modify it and keep on producing, but you must still produce the same as it was type examined and verified. That process is really important because it is in the complete European Union and even worldwide the standard process of getting clearance for safety relevant products. So you must have a factory which has a quality management system working. You must have type examination and verification in the design phase and in the starting production phase, yes, on series production. And later on, when you produce, you declare conformity. On the other hand, you can say you have the company itself. Then you have a notified body for the declaration of conformity. You have the type examination and verification, which is done in cooperation with the company and in cooperation with the notified body. And the annex declaration of conformity to type is done by the producer company again. So they just declare it's the same like it was. I give you an example from another case. When I was a young engineer, we did consultancy to one of our factories, and they had a problem with soldering. And so I told them, why don't you just use a better flux? Yeah, maybe a little stronger flux, and so you will have no longer soldering problems. And the manager, he just smiled and he said, we are producing for Volkswagen, and if we just change a little thing, yes, our complete process has been type examined and verified, and if we change only a little, like that flux, we have to go through all of the type examination and verification process. Yeah, we cannot do it. We must change it within the limits which are given us. Yeah, and that's something which is important here. Of course, some aspects in your company can be improved, but you must not change. You must not change the product really. Also, when in your production you have, for instance, some process, for instance, for detection of failures, yeah, or detection of failure causes. When you would omit such a thing, that also could mean your product is no longer conform to type. And that's something which is very important. So let's say that page 34 is very important for the understanding how you bring products into the market. That means you have the V model, that's the job you do as the manufacturer. But on the other hand, you always have an interaction with notified bodies, for instance, and with external accredited company or organizations. And in that way, you must get clearance for your product, and you also must keep up clearance for your product. That also means normally if you find some problem in the market, for instance, many people get an electrical shock, then normally the manufacturer should have to take actions, and also the legal organization should have to take actions. Unfortunately, the mechanism when such actions are not taken is very weak. Also, penalties are very low in such cases. And so that is some regulation which normally it is obeyed by most of the companies, because most of the companies are working according to law, except sometimes like Volkswagen, Audi, they do not. But normally they do. But the system is always not so, let's say, resilient against fraud, which is made purposely. That is a weakness of that system. Okay. The standards for medical devices. First of all, I said for the conformity, you have a quality management system, EN ISO 9000 to 9003 series, European norm based on International Standards Organization standard. That is general. The EN ISO 13485 from 2003 or later is relevant for medical devices. Also the EN 46003, which is a little special. For the risk management you have to do, it is described in the EN ISO 14971. That is important, and that is one of the most important questions in the verification is the and type examination is the risk management and the risk analysis according to that standard. To say it briefly, all of the techniques we have seen in this lecture for reliability analysis and for risk analysis are important according to that standard. And in that way, all of the techniques which we have seen here should enable you to do a risk management according to that EN ISO 14971, at least in principle. There are amendments to this, and that is the core part which also has connection with our lecture here. Another thing is the biological evaluation of implantable medical devices. So these are described in EN ISO 10993 and 30993. One thing is the damaging effects to the cells and biological substances, which is a result of the contact with the device or its material. It must be evaluated according to these standards. So there is a certain list of materials which has clearance according to these standards. As I mentioned, titanium, gold, some polyamide by some manufacturer, silicone by some manufacturer. And so Professor Stieglitz, for instance, from the biomedical lab here in the IMTech, most of his work is assembly and packaging for medical implants. The difference is I do general assembly and packaging. I can use any material. Professor Stieglitz can use only materials according to these EN ISO standards. Other materials would not be allowed, or he would have to go through all of that biological evaluation, and normally a small university lab cannot afford that. That is something which the manufacturer of that material should provide. And in that way, the number of materials for doing research on implants is also limited, because it only makes sense to investigate materials where you are sure they later on are allowed for real implants. Okay. Here I will not go through all of the details. There are some more things, for instance, how to sterilize it and so on. You will not have to keep in mind all of these. You will not have to keep in mind all of the standards with their numbers, but for me it's more relevant that you understand how the general process is to get products into the market. Okay, maybe a last remark for the risk management, which is described in the ISO 14971. It is to do risk analysis. So that is what we have done in our lecture here. Then the risk is evaluated. So what is the severity of each hazard? And there are also acceptability decisions. So will it improve the patient's situation or not? Then we have risk control. That is important because risk can be controlled in three ways. One is reduce probability. Second is reduce effect. And the third is take additional actions of risk control, as we have also seen in automotive industry. And it is important to repeat this over time, and also changes must be monitored, and also risk management comprises post-production information. That means we must actively collect information in the phase after the product is in the market, in order to get feedback and to re-evaluate the product if really all of the assumptions we have taken in the design process are realistic, or otherwise we would have to take actions. The actions could be accepted as it is, or take the products out. For instance, that's an important thing. Implants sometimes have to be built out of the patient, and that is not such a pleasant situation. If you think your implant will work for 20 years and after 3 or 4 years it has to be taken out again, that means additional risk for the patient. And in that way, we have come back to risk, and risk is now, initially it was defined by the severity times the probability, but in a modern way, risk is described by severity, by probability, and by the risk control, or let's say the probability that risk control will be effective or not. Okay, in that way, we are finished with the lecture. That's all I wanted to teach you. From the next week on, I would propose that we go through exercises. I think now we know it all together, and on that basis we could go through also again through mathematical part. Let me again repeat that the initial equations on reliability functions and so on are really important, and these are something which is also the basis for the understanding of many of the aspects which have been described here in a more qualitative way. Okay, maybe you can take a look at these initial mathematical parts, and we will meet next week again in order to start with exercising and preparation for the exam. Okay, thanks for your attention and goodbye.